And today we have an interesting problem for us to solve. This problem is just specified by two parameters n and r, both of which are positive integers. The problem starts by asking us to consider the set S, which is just the set of the first n natural numbers. So it's this simple set. And then it asks us to consider all possible subsets of this set S, which are of size r. So, which are smaller subsets of this set. So, we should collect those subsets. And then the problem asks us to look at the smallest element in each of those subsets of size r. And once we collect those smallest elements, it claims that there is a very simple expression for the average smallest number in that collection of subsets. That's a startling claim, and let's see it concretely before we really let it sink in. So let's say n is 3, and let's say r is 2. A very simple and small example. So our set S will just be 1, 2, 3. And because the problem says r is 2, we should like to collect a subset of subsets of S which are of size 2. And that collection would look like this. So these three elements here are the three subsets of the set of size 2. And remember, it then asked us to sum up the smallest elements of each of these sets. And it says that the average of the smallest elements must be a simple expression. And you know what? This is what the problem claims. Given n and r, if you do this computation, if you follow these steps, the claim is that that average, which maybe I can denote it by s subscript nr. So that average given an n and r is just this, and which, by the way, for us happens to be 4 by 3, which, if you recognize, is indeed n plus 1 over r plus 1. This is a very non-trivial steps that we did, a very convoluted steps that we did here, and we came up with something which is so clean: n plus 1 over r plus 1. How do these even combine together? How does doing something so non-trivial end up with something so clean, n plus 1 over r plus 1? Let's take one more example, and maybe that'll help us see some insights. So let's take something slightly bigger. Let's take n equals 4, and maybe let's just take stick with r equals 2. So this time our set S is this, and the collection of subsets is this. So we have all the ones starting with a 1, all the subsets starting with a 4, and the lone ones with a 3. And if I were to sum up the smallest elements, I'm going to go ahead. There are three ones, so that gives a contribution of 3. There are two twos giving a contribution of 4, and there's a single 3. And how many of these are there? There are 3 and 3, 6 of these. So this sums up to 10 over 6, which, if we simplify, should come to 5 over 3, which again, unsurprisingly or surprisingly, is n plus 1 over r plus 1. So, what here is the relation between this right hand side here and all the mumbo jumbo that we did on the left hand side? And where that's exactly why I think this problem is very interesting. Where do we even start? What's the connection? And I think that's actually a good place to start. And that's what makes this problem good. That's what makes this problem interesting and worthy to solve, is precisely because we end up at a place where we say, okay, now where do we even start? So let's see what we're asked to solve. I'm going to scroll up a bit. So we're asked to solve. we said there's some kind of an average, and I'm going to call it this average quantity equals some expression on the right hand side. Now, um, if this is an average, I should be able to write it down as sum over the number of such terms, right? So if this is an average, what can I write it down as? So maybe let me denote some number. Maybe I'll just call it capital X. Capital X, which denotes the sum of the smallest elements in each of the subsets of size R. If that's capital X, then in the denominator, if we have the total number of such subsets, then that precisely is the average. And how many subsets of size R do we get from a set of size n? And that is a pretty standard results. It's n choose R, and n choose R, just to refresh our memory, is just a fancy way to write the factorial of n over the factorial of n minus R times the factorial of R. Okay, then I see something interesting. Hey, this looks like n choose R, and here is n plus 1 over R plus 1. Hey, what if I were to do this? What if I were to say this is the same as saying, well, x equals n plus 1 over R plus 1 times n choose R. And if you believe me, if you believe that this is equal to this expression, then this thing combined with this is actually n plus 1 factorial over R, by the way, R plus 1 factorial times n minus R factorial, which actually happens to be n plus 1 choose R plus 1, following this notation here. Huh. So suddenly, uh, we might have transformed the problem, which talked earlier about averages, to something that talks about the sum of some numbers. So again, to refresh our memory, x here denotes the sum of the smallest elements in each of the subsets of size r. So maybe it is also helpful to designate x with n and r, because x depends on the values of n and r. Okay, so then this on the left hand side is a sum of numbers. And what is this? The thing on the right hand side? The thing on the right hand side just seems to be the number of ways I could choose r plus 1 distinct things from n plus 1 distinct things. So on the right hand side seems to be something that results as a outcome of counting. And on the left hand side we're adding something. So a sum of a bunch of numbers, how does that even relate to counting something, counting a larger set? Is there a relation between this and this? Can we do something that transforms adding a bunch of these numbers into counting the number of subsets? Hmm. Maybe you want to pause here. Pause, reflect, think about it. Can you find a connection here? And if you have paused or haven't, I'm just going to continue. So, this is what I could do. I'm just going to concentrate on the right hand side, because I know if I can prove that this thing equals the sum of the smallest numbers in each of the subsets of size r, then basically that's what I've proven. Okay, so let me go, because on the right hand side is a pretty easy thing for me to visualize. What is this? It's just the number of subsets of size r plus 1 out of a parent set of size n plus 1. Remember, r was less than or equal to n because of our the structure of our initial problem. So r plus 1 is also less than or equal to n plus 1. There's nothing wrong with this expression. Okay, so what I'm going to do is this. The initial set that I had, the set of first n positive natural numbers, I'm going to augment that, and I'm going to add a 0 at the beginning. I forcibly make this now a set of size n plus 1. Okay, so this is a set of size n plus 1. And out of this, let me see what are all subsets of size r plus 1. How do they even look like? So let me maybe write down a few. mm, this is my just, oops, maybe not 3, maybe just maybe I call it n. So this is a subset of size r plus 1. You just have to take it from me for some size r. And what I'm going to do is I'm going to find out the subsets of size r from our initial set, the parent set, which is the set 1 to n, and try to see if there's a relation between these two things. So let's see. From our initial set of size n, let's say I have created sets like this. Maybe it's a 1 and a 2 and something and on. And each of these subsets of size r, this is a subset of size r, I will write down in increasing order. Why do I do this? I think it will become apparent in just a minute. And maybe let's do this one. The next one might just be 2, 5, 7, blah, blah, blah. Again, this is a subset of size R. And just let me just write one more, and that will drive the point home, I think. Maybe the next one is 3, 7, 9, so on. Again, a subset of size R. And this is the entire collection here. And how many of these are there? Well, we just discussed. These are n choose R of these guys here. Now, notice something interesting. In our sum, the way we are calculating x sub n comma r, this guy gives a contribution of 1. Okay. This guy gives a contribution of 2. And this guy gives a contribution of 3. Right? Because these are the smallest elements. And we are going to sum up 1 and then 2 and then 3. And then whatever happens to be the smallest elements in each of the remaining subsets. Can I somehow relate this 1, this 2, this 3 to these subsets here? Because that is what the equation is almost prompting us to do. It's prompting us to relate the sum here on the left hand side to just counting subsets on the right hand side. And it seems that it is actually hinting us to this. So consider this set. It's a set of size r. What if I were to add a 0 at the beginning? It immediately becomes a set of size r plus 1. And obviously, because it is a set of size r plus 1, of elements start ranging from 0 to n, then it must be in this list of sets that we were writing. In fact, it might even be this one, a subset of size r plus 1. Okay. So it turns out that adding a 1 is just basically saying I'm counting this one subset. So, okay, quickly, let's come to this guy. What does this imply in the same vein? Well, in the same vein, it implies this guy, which contributes to 2, actually points us to two different subsets in this list. Can you guess which those are? It's exactly the two subsets that can be formed by augmenting the two numbers that are smaller than 2, which are 0 and 1. So there is this one subset which is exactly augmented by adding a 0 before this very set. So the remainder of the set is exactly the same as this one. I've just added a 0. This now becomes a subset of size r plus 1. So we must be have that guy in this list. And the other one is the one which is formed by augmenting and adding a 1. Oh, and if you note, the same thing happens for this guy, which has a 3 at the beginning. Its contribution in our original sum x is 3, but that is the same as saying it is pointing to 3 subsets in this list. And which are those? I think now, from by now it's clear. You copy the same set from the right hand side and just add the 3 numbers which are less than 3. So it's the one which is formed by augmenting a 0, by augmenting a 1, and by augmenting a 2. And each of these sets, because I'm augmenting one number, from a set of size r becomes a set of size r plus 1. And because it's a subset of size r plus 1, and each of the numbers is a unique number between 0 to n, including 0 and including n, then whatever we augment must actually be a subset of size r plus 1 of this set, the set of non negative integer numbers between 0 and n. And so suddenly we see that if we were to count just the number of such subsets of size r plus 1, it is the same as counting the smallest number here. Because if I were to count all of these, which are maybe just one, two, three, four, five, six of these, that and those are just the ones I've drawn here. There might be more. Counting just the six of these, I hope you now realize is actually counting this one plus this two plus this three to give six. Because adding this one is the same as checking off this. Adding a 2 to the sum x is the same as saying I have counted this and I've checked this. And adding this 3 to the sum x is just saying I'm adding or I'm accounting for these subsets. So adding the smallest element of a subset we have just shown is equivalent to counting the number of subsets in a slightly different problem. And then that probably helps us solve this. Should we check? That actually does it. So what we have just shown is actually this, that x sub n comma r, which is just the sum of the smallest elements in the subsets of size r taken from the set 0 to n, is the same as just counting the number of sets of size r plus 1 from a set of size n plus 1. And then from there, we just backtrack. We decompose this as this. We come over to the right hand side, bringing this guy and choose r to the right hand side, and then my sum over the total becomes an average, and we reach the original problem. The original problem stated in this way was actually it still is pretty startling. How do you even go ahead comparing or computing the average, and that too a very non-trivial average? It's the average of the smallest elements out of the subsets of a particular set, and that happens to be this expression. How do we go about doing that? Well, we went about by first noticing that I can write the average as the sum over the total number of subsets which I know how to calculate. And from there, one thing led to the other. And we saw that now we are faced with the problem of somehow trying to relate the sums to counting the number of subsets. And then that is what actually led us to the problem. That is to the solution of the problem. So, what I think we would like to take away from this is, well, when we have the problem of counting the number of elements in a set, counting some set, if I have to count a set A and I'm having difficulty in counting these sets, the number, sorry, I'm having a difficulty in counting the elements in this set, then if there is another set B, which I find easier to compute in terms of the size, which I find easier to count, and if I can somehow create a one-to-one mapping between A and B, so I don't care anymore that I am not able to count A. I can just count B, and I can use the fact that for every element in B there is an element in A, and every element in A has an element in B. So I have a one-to-one mapping, exactly one-to-one mapping. Whenever I have a one-to-one mapping between two sets, counting one is enough because the count of the other set is the same. And that's what we used here. We transformed the problem and we created a one-to-one mapping between what these numbers here mean, the number 2, the number 3. They actually meant the exact number of subsets on the left hand side. So we use that, and I hope you find this interesting because um, this technique actually comes in handy a lot of times in a lot of different variety of places. So I hope you find this problem interesting, and I'll keep sharing more. Thank you. See you guys later.